Today we're on page 3 of the chapter 15 AP Chemistry packet. We're going to continue talking about buffers and what happens when you add acids and bases into buffers. We're going to start with the first example with NH3 and NH4 plus. Into this you're going to be adding H plus. So to understand this, let's first talk about the beaker by itself before you add anything into it. You're going to have in this beaker both NH3 and NH4 plus, which you should recognize as a weak base and as conjugate acid. Let's find the pH of this beaker by itself right away, just to find out what it is. So I'm going to use the buffer shortcut, since it's a buffer, for hydroxide. So that's hydroxide equals Kb times B over A. So we'll write this out. The Kb is 1.8 10 to the minus fifth for ammonia. The base is the ammonia, which is the 0.8. You can use molarity for this, so 0.80 divided by the acid, which is the 0.7. So that's going to be 0.7 over here. Then you're going to do your math, and it's going to be 2.1 10 to the minus fifth molar. And remember, that's the OH, so when you negative log and 14 minus it, you're going to get finally a pH of 9.31, which is basic, which makes sense because this is a basic buffer. So this is the beaker by itself. Before you add anything into it, this is the buffer's pH of these two. Now let's say we add H+. The first question you always ask, is there a reaction? So is there a reaction? The answer is yes. You just say yes, stoich in moles. So is there a reaction? Yes, stoich in moles. So we do stoich in moles. So you have to figure out what the reaction is going to be. You're adding H plus into this. So the H plus is going to react with the base of the buffer because H, of course, is an acid. So the base is the NH3. And when you look at this, you could see that it's going to make NH4 plus. Then we write in our moles. So the H plus has a 0.03. This is going to be limiting reagent. Don't forget ICF. 0.030 moles, 0.80 moles for the ammonia, and 0.70 moles for the ammonium. This is a classic mistake that a lot of kids forget to write this in the beginning. Don't forget, since it already is a buffer. So the running out is going to be the H plus. We're going to subtract 030 from the left, each thing, and add 030 to the right. So when we're all done, this is going to be a 0, this is going to be a 0.77, and this is going to be a 0.73. And now you ask yourself, what do I have? If I have a weak base and its conjugate acid, the answer is I have a buffer. So since I have a buffer, I'm going to do the buffer shortcut. So I still have a buffer. Even though I added H plus into the beaker and I changed a bunch of ammonia into ammonium, I'm still left with some of each in the beaker. So I do still have a buffer. So since I have a buffer, I'm going to do the buffer shortcut. And we can use the same one we used before. So I'll just write it over here again. OH minus equals Kb times B over A. The Kb is still 1.8 10 to the minus fifth. The base, remember, is going to be the ammonia. So that's the base, which is going to be 0.77. And then the acid is going to be the 0.73. 0.73. And when you do the math, you're going to get a OH minus of 1.9 10 to the minus fifth. And then you negative log and 14 minus, because that's the OH, remember. So the pH is going to be 9.28. And notice how that compares with the 9.31. The delta pH went down by 0.03. So it went down by 0.03 as compared with the original pH 9.31. Okay, it makes sense it went down because we added an acid, so it made the pH go down, but not significantly. Okay, let's do the same problem again, but now we're going to add OH minus. We'll do that on the next video. So just continuing on the same video, I was having a little trouble before. So let's try this one with the buffer in here again. This is going to be NH3, and we're going to have NH4 plus in here as well. But now we're going to add hydroxide. So when you add hydroxide, you have to ask yourself, is there a reaction? And the answer to that is yes. And when you say yes, you stay stoic in moles. So yes, stoic in moles. So you must figure out what the reaction is. So the hydroxide is going to find the acid part of the buffer. Since OH is a base, we're going to find the acid. The acid is NH4 plus. So that's going to make water and NH3. Water and NH3 are going to be formed. And we're going to do ICF. Let's write down all our moles. This is going to be 0.030. This is going to be 0.70. And again, don't forget to write down the initial amount of the ammonia because there is a buffer present. It's both parts. The OH minus is going to run out. So minus 0.03 plus 0.03 on the right. When all is said and done, you ran out of the hydroxide. You have 0.67 of the ammonium, 0.83 of the ammonia, and you're going to ask yourself, what do I have right now? I have a buffer because I have both the weak base and its conjugate acid. So the buffer shortcut, again, is going to be OH minus equals Kb times B over A. You could always just do the Ka shortcut. You just got to find the Ka yourself. So whatever you prefer doing is fine. So we're going to do the Kb is 1.810 to the minus fifth. Now you look for the base of the buffer. That's the 0.83. That's going to go in the numerator. Then you're going to look for the acid part of the buffer, which is the 0.67. That goes in the denominator. Do your final calculation. You get 2.210 to the minus fifth molar. That is the hydroxide. You're going to negative log and 14 minus that. And so you're going to find the pH to be 9.35. And that's a delta pH of positive 0.04 because we added a base. It makes sense that the pH went up. So the original pH was 9.31. This went up by 0.04. Okay, when we added a base, but remember before it went down by 0.03 when we added an acid. It was the same amount of acid and base. Again, why did it go up more? Why did it go up more than it went down? This threw me off for a second, but we're back on track here. Sorry about that. This went up more than it went down, which is surprising because we said earlier that when you add a base into a basic buffer, you would expect it to change less. However, here's the difference. This has 0.8 molar of the base and only 0.7 molar of the acid. So see how there's not as much acid part of the buffer as the base. So if there's not as much acid and you're reacting a hydroxide with the acid portion of the buffer, it's not going to withstand the change as well. So this happened to change by 0.04 versus the other one that changed by 0.03 because the other one we were adding H plus that reacted with the base. Since the base has a higher concentration, it can withstand adding an acid better than it could have stood withstanding adding a base. So that's why this one happens to be less of a change than that one, whereas in the previous pages of the packet when we did the acetic acid, they had the same molarity, the acetic acid and the sodium acetate. So that's why with the same molarity, it came out the other way. Lastly, we're going to talk about buffer capacity. Buffer capacity refers to how much could you add to the buffer in order to not ruin the buffer. So let's take a look at this buffer. It's exactly the same as we did earlier in the notes, except now we have a 5 molar and a 5 molar instead of the original one on page 2 of the notes where we had a 0.5. So 0.5 was on page 2. We'll compare that in a moment. Okay, so let's do the same thing again. We have an acetic acid buffer. So we're going to write we could just write here HA and A minus to make our lives a little bit easier. We're going to add H plus to this. We ask ourselves, is there a reaction? The answer is yes, stoich in moles. So we write the stoich in mole reaction. The H plus is going to find the base part of the buffer, and it's going to react to form back the HA. We're going to do an ICF chart, and we're going to write down 0.02 here. And then the A minus and the AHA are both going to be 5. Oops. They're both going to be 5 because the molarity is 5 and the volume is 1. So you do molarity equals moles over liters, and you get 5, so minus 0.02 plus 0.02 plus 0.02. Now with sig figs, I didn't line these up too well, but sig figs, this is still going to just pretty much come out to be 4.98. I'm getting a little sloppy with sig figs here. Okay, technically it should be 5.0, 5.0, but even if we do the 4.98 and 5.02, let's just see what happens. Okay, so what do we have? We have a buffer because we still have acid and conjugate base. So we do the shortcut. I'll use the H plus shortcut since we know the Ka. Ka, A over B. The Ka is 1.8, 10 to the minus fifth. The acid is the HA, 5.02. The base is the 4.98. That goes over here. And interestingly, when you do the math for this with sig figs, you're going to find out that the H plus is going to come out to be 1.8, 10 to the minus fifth. And the pH of that is going to be 4.74. which is the exact same pH as the first page on page 2 of this. So there's no change in pH. So here it is. You added H plus into a buffer, and this buffer did not even change pH at all. And the reason why this one did not change at all, and page 2 it changed by a little bit, is because this is 5 times as concentrated as the one on page 2. So because this buffer has a very high concentration compared to page 2, it has a higher buffer capacity. It could withstand the adding acid and base better. Okay, so you're not going to wreck this buffer as easily as you would wreck the buffer on page 2.